This would be a crossed aldol reaction because we're starting with aldehydes, not esters. If they were esters, then it becomes a Claisen. Right? The result of this reaction, what do we get? Anybody remember? Okay, we can find it, sort of. Okay. We get 4 different results because there are 2 alpha hydrogens that we could potentially react, which then means we get 2 nucleophiles, and we have 2 electrophiles, which means we can get all those possible combinations. That means we get a giant mess for our possible products. Right? For that same reason, when we move to the Claisen, we could potentially run into issues. Or, sorry, our solution to it, we had a couple solutions. One, run 2 separate reactions. In this case, by running sodium hydride first, sodium hydride being a stupidly strong base, will react all of the aldehyde across it to make the single nucleophile. So I only get 1 nucleophile. If I then follow that up with the second step to bring in the electrophile, I only get 1 electrophile. Right? The reason the top reaction produced so many different products is that I have just a strong base, which means only some of it removes the hydrogen. If only some of it removes the hydrogen, then some of that compound still has active electrophile. Right? That's the problem with that. By going to sodium hydride with a stupidly strong base, we completely convert all of our starting aldehyde over to the nucleophile. And because it is stupidly strong, I get no electrophile left over. That carbonyl carbon is resonance stabilized by the nucleophile, which means I don't get a good electrophile. Okay? So I get 1 nucleophile followed by the next step of the reaction, 1 electrophile. Okay? There is still some limited acid-base deprotonation to get another nucleophile, but again, that becomes more limited in the extent, and we end up getting mostly 1 product. When we move to the Claisen, we're going to encounter similar issues. So if we go with a crossed Claisen, why is this one known as a crossed Claisen? They're 2 different esters. Okay? When we move to a crossed Claisen, we have the same issue. Notice the base that I'm using matches the leaving group in both my esters. Okay? Again, I need that to be the case, otherwise I get a mess of possible products. Okay? That is now also a weak strong base, for lack of a better descriptor, which means both of those alpha hydrogens are possibly accessible, which means 2 different nucleophiles. 2 different nucleophiles, 2 different electrophiles. I get a giant mess of possible products. So the same solutions that happened in the aldol for us trying to prevent that mass of different products is we go through and we change some of those conditions. One of those conditions is making sure that one of your esters has no alpha hydrogens. So your textbook gave you a nice list of possible examples. Okay? Diethyl carbonate, does that sound familiar to anybody? In the lab? That made a Grignard dye? Oh, that was one of the reagents that we used. Yep. Okay. Diethyl oxalate. Not quite. We used something similar. We used oxalochloride. We used chlorides instead of the oxygens, okay, as leaving groups in our chemiluminescence. Okay? So these chemicals have slightly different, or have different chemistries in that they don't have alpha hydrogens. No alpha hydrogens means all of those esters will exclusively act as electrophiles. Which means when I go through under the conditions shown below, I don't have to worry about that first structure. This species can only act as an electrophile because there's no hydrogens to remove. So that when I mix it with the base and my other ester, I only get one nucleophile. Okay? This is going to limit the amount of side products that can come out, and we would expect a higher yield. Notice, what is our yield? 45%. Why is it so horrendously low? Our ester that can act as a nucleophile is reacting with a weak base, okay, or a weak strong base, which means some of it maintains the electrophilicity. Okay? So we can get some side reaction of our nucleophile attacking similar esters. Okay? Other issues with it, our oxygens or our base could act as a nucleophile as well, limiting the amount of products coming out of it. Yes, it just cyclizes and does the same result, and we end up forming the same compound, but it reduces the amount of possible things that come out of it, or successful interactions. Okay? If we up the amount of time, that can help with some of this in net yield, but it can only help to achieve our equilibrium. Yes?
How would this give us just one product versus the other one, which gave us four? Because that aldehyde hydrogen, I don't think you can remove that.
That is absolutely right. We cannot remove that, which means that species acts as an electrophile, and an electrophile only. It can't act as a nucleophile. We move over to the other species. It has alpha hydrogens, which means that species can act as a nucleophile. In the previous reactions, I had 2 electrophiles, 2 nucleophiles. I get more products. Here, only 1 electrophile. Only 1 nucleophile. That's what limits this. Okay? Again, what we just pointed out, our nucleophilic species, because we're under weak base, I keep calling it weak base, just strong base conditions, that nucleophile can be potentially electrophilic. That might be accounting for the loss in yield, is that our nucleophile species is attacking other unreacted species. Okay? Okay? So, what happens in this case? Why is this one different?
You have alpha hydrogens and an electrophile in the first one.
I have alpha hydrogens and an electrophile. Okay? I'm going to argue we do not have an electrophile. Why do we not have an electrophile? What are you suggesting is the electrophile? The carbonyl carbon. Why is that carbonyl carbon not an electrophile? So is hydroxide. Hydroxide, I have an electrophile.
Yeah, but that's a strong base.
So is hydroxide. This is the issue with our terms.
Stronger base than hydroxide.
That's a stronger base that's on our stupidly strong end. Because it is stupidly strong, what happens? It is an irreversible acid-base reaction. So it quantitatively converts my starting ketone over to a single nucleophile, and I don't get any of that electrophile intermediate. Which hydrogen does it remove, A or B? Okay, the suggestion was for B, which means the product we're forming would be here, right?
Hold on, but isn't it stupidly strong base, or what kind of base is it?
Good question. Isn't that a stupidly strong base, or what kind of base is it? I'm going to start with your first statement. Isn't that stupidly strong? Is NH2 a stupidly strong base?
It's just stronger.
I don't think
It's not stupidly strong. It's
It-
just stronger.
Qualifies as our stupidly strong. It is effectively LDA. Okay, the only thing that makes it different is what?
It doesn't have.
It's not as bulky. It has the same chemistry. Okay, because it's still a negative nitrogen. At being stupidly strong, what does that suggest for our enolate that comes out of this? I should get the kinetic product. Do I remove HB? No, I actually remove HA. Okay. This is where focusing on the chemistry, not on the specific reagents, helps out. Okay? Which means I form my nucleophile. Now what happens? I now have a strong nucleophile. What do I need to react it with? An electrophile. There's step one with our electrophile. Notice that Cardi drew a nice little arrow for us, pointing where? At the alpha position. Why might we be drawing attention to the alpha position?
He's asking us.
Yeah, but I usually follow it up with an answer. Why might we be drawing attention to the alpha position? There's acidic hydrogens. What could, if we removed those acidic hydrogens, there would be resonance to stabilize it, which means I would then have at that position a negative charge, which is a nucleophile. I'd have competing nucleophiles. Why am I not concerned about that?
Because we're following it up with an acid work.
Nope.
Because we already have the negative charge.
You already let those two react, and then you put that in more resonance in the ester, so it's
Okay. More electrophilic is an interesting concept. That's talking about this carbon. What I just asked about was this carbon. Why do we not care about those alpha hydrogens?
because there's no base to take it away. If that strong base already worked.
Isn't a negative charge a strong base?
Just because that oxygen's also resonating inward, so it's like competing ions.
The oxygen from the ester is resonating inwards, meaning if I remove those hydrogens, they are less acidic than the starting ketone. Because they are less acidic, do I care about the alpha hydrogens? No. For those of you going, wow, that's a really hard question, it is. It's a question that's shown up, I believe, on every single one of the exams. Looking at the acidity, difference in acidity between a ketone and an ester. Okay? I cannot stress enough how incredibly important that ranking is. You need to be able to understand that. You will absolutely see at least one question referencing the difference in acidity. Okay? It is still consistently one of the most missed questions because you're immediately jumping to induction. Induction is the last thing to look at. The resonance of that ester stabilizes the electrophile or stabilizes the positive, making those hydrogens less likely to be removed. Okay? It is of critical importance because that's what drives your Claisens. It drives your aldols. Okay? It drives literally just ranking acids and bases. Okay? Super important. You have to be able to use that ranking system that starts with charge, size, electronegativity, resonance, induction. And notice it ends on induction. If you get to a system where you think, oh, I think these are different based off of induction, you're probably wrong. Okay? Because that is the last thing to evaluate. Okay? So we've got a good nucleophile. The nucleophile attacks our electrophile. What breaks? Because I would now exceed the octet on that carbon. The pi bond breaks. The result Yep. There was kind of a question. Now what happens? It comes back down and kicks out the leaving group. the result, whoops, what also has to happen? Because that looks an awful lot like the answer, doesn't it? Yes, it does, because it's the same thing. I even color-coded exactly the same, except I drew in the purple to show the bond connection.
Hydrogen needs to come off because those are all very...
A hydrogen must be removed. We're running under the Claisen conditions. Under Claisen conditions, that reaction does not happen. The equilibrium heavily favors the reverse reaction, meaning I would not get product until we remove a second alpha hydrogen. That second alpha hydrogen is what now generates a resonance stabilized structure. That resonance stabilization is what drives this reaction forwards. Do I want to end with that charged species? No, so what do I have to do? Put a hydrogen back on it. But if I put a hydrogen back on it, I'd have to be under acidic conditions. But I'm under basic conditions. What do I have to do? Second step, H+, and it takes me back to that material. There's my final answer. The only reason the Claisen works is because of that second alpha hydrogen. Without that alpha hydrogen, Claisen does not work. Referencing it as middle becomes questionable. Where's the alpha hydrogen that I'm talking about? Here's the first one. Here's the second one. Okay? It's all a question of reference on where you're going at it. If you start saying the middle alpha hydrogen, well, that carbon came from which of my structures? That becomes harder to track. Target it back to the nucleophiles and the electrophiles because that's what's driving the chemistry. That can help ensure your proper connectivity. Okay? Just like with aldols, we can do intramolecular reactions. Okay, so we can get a Claisen cyclizing back on itself. Okay? Why on earth does this deserve somebody else's name? I don't know. I've got no special answer for you except that it is. It's now known as the Dieckmann condensation. Okay? The Dieckmann condensation is just an intramolecular Claisen reaction. Okay? So we start with a compound that is a diester. It has to be a diester because to do a Claisen, what do we need? 2 esters. Okay? So if we're going to do a Claisen condensation that is intramolecular, a single molecule must have both ester functionalities. Why is the cyclization allowed to happen? There's enough carbons in the ring that we minimize ring strain. 1, 2, 3, 4, 5. Okay. Is it important to go through and number those carbons?
Maybe 6.
Yeah, I double-2'd. I thought it was coming out to 6, and I couldn't quite figure out why. Couldn't do it.
Do we count the carbon under the first double bonded oxygen?
Why do I not count the carbon under the first double bond oxygen?
I need a nucleophile.
We need a nucleophile, just with like all Claisens. It's a nucleophile and an electrophile. Once we've established that I have a carbonyl, there's an electrophile. Where's the nucleophile? The nucleophile will have to be negatively charged. There's no obvious negative, but we've got a base. What is the base going to do? Deprotonate, making a nucleophile. Okay? That acidic hydrogen is at the alpha position. So what I'm looking at trying to do here is draw just the cyclized structure. 1, 2, 3, 4, 5, 6. Okay? Once I've drawn the ring, now I can throw in all those other pieces. At position 1, do I also have a carbonyl attached? Yeah. So at position 1, I can draw that carbonyl piece. Okay. What's at position 6? The other piece, O minus and OET. What functional group is circled in blue, or approximative functional group? That is a hemiacetal. What do we know about hemiacetals? They are unstable and do what? Revert to? I would stick with carbonyl, not necessarily ketone. That depends on where you're located. Right, so that means the electrons come back down to form the pi bond. I've exceeded the octet, so I kick out the leaving group. Okay. For this to happen, what do I also have to have in this structure? I had to have 2 acidic hydrogens. Do I still have an alpha hydrogen that could stabilize the structure? Position 1, there's still an alpha hydrogen. Because that alpha hydrogen's there, I know this was allowed to happen. As long as I know it was allowed to happen, I could then say this was my final answer. I don't have to draw all of those intermediates. Does that make sense? Yes?
You can only do that for part of the 6 ring, right?
6
5?
or 5. Why 5 or 6?
They're the most stable.
They're the most stable. This goes all the way back to Unit 1 when we talked about cyclic structures. 5 and 6-membered rings are the most stable. Why are 6-membered rings the most stable? There's less steric strain, because what does that structure do? What does it look like? A chair. Are you responsible for chairs on the ACS exam? Yes, that's first semester material. You need to know that information. Okay? Make sense? I think that answers your question. Yeah. Okay. You'll notice that this structure looks slightly different than what I had drawn, right? Yeah, what was the difference?
Year 1 was year 2.
Okay, we flipped it over itself. Okay, so they were effectively mirror images of each other. Don't stress a whole lot on that, but realize that depending on how the ACS decides to draw out their structures versus how you draw out your structures, they may look slightly differently. You are responsible for that 3-dimensional mapping. Okay, that takes practice. Okay. The textbook then jumps into the malonic ester and the acetoacetic ester syntheses. Right? Yes, I have to look at the slides when I go through and say those. Right? What is different about these 2 structures than the esters that we looked at before? I have an alpha hydrogen in between. Don't I also... go away. Don't I also, at least for the acetoacetic ester, don't I also have an alpha hydrogen at the end? What is important about those 2 structures? It's not just that we have the alpha hydrogen in between, it's that these alpha hydrogens are more acidic. Why is that important? Faster, better. What do you mean faster, better?
The hydrogen more acidic will come off easily.
More easily, which means I don't have to use as strong a base. Okay? So these tend to be more important for syntheses than our Claisen or our aldehydes, because we now have a stronger acid, which means I can use a weaker base to pull that hydrogen off without having to stress about side reactions. We're making those 2 sites that they've got labeled alpha on the slides here our nucleophile. Okay? So we go ahead and we remove that hydrogen. Notice the textbook's throwing in the squiggle. What's the squiggle mean? The structure just goes on. What does it goes on to? It doesn't matter, because the chemistry is right here. It's just connecting to something else. And everyone goes, oh, that's silly. Why are you making a big deal of that? Because the instant I draw something else there, you get the question wrong. Because you're like, well, this something else is... No! It's trash. Focus on the chemistry.
But you also do that sometimes.
I will draw something else out there, and what does it do? Distracts you by doing nothing. Focus on the chemistry. The chemistry's right there. Keep your focus there. Right? You do have to carefully evaluate, but don't start spending a whole bunch of time in trash areas. Look for the commonalities. Right? That is hard, but that comes with practice. Again, once we've removed it, we now have our good nucleophile, and we can run what type of reaction? SN2. How'd you know that? Okay, how else did you know that?
Well, because
I don't accept you studied it. That's not a bad answer, but I don't accept that. What about what's shown here makes you go, yes, I agree. Cardi didn't screw up. That is indeed SN2.
because bromine's a good leading group, and there's a whole bunch of other stuff. So in order to get in there with all that steric hindrance, it has to do with backside.
So you're referencing steric hindrance, which I would argue is a good statement. Unfortunately, it's a little bit questionable here because our steric hindrance refers to really the electrophile, so that carbon. Okay. Do I know what is connected to that carbon?
Doesn't it have to force that stuff to leave?
It has to force the bromine to leave, yes.
It's connected
Do
to
I know what's connected to that carbon?
I have no idea, it would be 6 million things there.
You have no idea because it's specified as an R group. Right? So while I agree trying to decide an SN2 by looking at steric hindrance is a good idea, can we look at steric hindrance to evaluate why this is an SN2? No, because we don't know what the substrate is. Without the substrate context, we can't say steric hindrance is what's preventing this or what's allowing this. Okay? So how do we know this is SN2 if we don't look at the substrate? Well, substitution, we have 4 things to evaluate. Sorry, it took too long. You guys got to go through the 4 things. Substrate, nucleophile strength. Those are being like, God, I've never learned this. You did in first semester. You're responsible for it. You will be asked questions literally about this concept.
Leaving group?
Leaving group ability. Primary, secondary, tertiary is the substrate argument. Not acidic or base, right idea on the conditions, solvent. Okay? Those 4 primary pieces you need to consider and look at. Are you told what the solvent is? No. No, so solvent's not useful. Do you have a good leaving group?
Yep.
Yes. Which substitution reaction does not need a good leaving group?
Oh, no, all of them.
Trick question. They all need a good leaving group. Is leaving group ability useful to look at? No. So there's really only 3 things you got to evaluate. Substrate, nucleophile strength, and solvent. Substrate, not enough information to draw conclusions. Solvent, not given.
Leaving group.
We just said leaving group doesn't count. The nucleophile strength. What is our nucleophile here? It is strong. How do we know it's strong? It's negatively charged. Okay? That is why we're running under SN2 conditions. So because I'm thinking SN2, which substrate do you think would be best? A, B, C. That's a B. Why C? How do you know that's primary? Isn't that connected to the ring? It's connected to the carbon. Common misconception again. You end up deleting that carbon. That is a primary substrate. Okay? Everything in that reaction, first semester. Why is it showing up in second semester? What's that? It's not so much everything's connected. I would argue all of that is first semester. Okay? The reason why this gets saved for second semester has to do with this. Why are they so special? Why is this synthesis, that product, important? Why do I care? Okay? I care not because of any of that, but because what happens afterwards. That structure on the left is our result of the malonic or acetoacetic ester synthesis. What happened in this reaction? I made a carbon-carbon bond here. Okay. In this step, I broke one. In the previous one in the synthesis, I made a carbon-carbon bond, but that was one that was standard. Nothing about that was new or fancy. This is where it gets new and fancy. What did I do? I broke it. Broke what? Which carbon-carbon bond? This one? I'll accept that. Okay. We broke that one. This whole piece somehow disappeared. Okay? So let's consider something about the reactivity around that, because this chemistry could be difficult to go through and process. Where do you expect those electrons to go? You're expecting them to go to the ketone, so I'm going to say that's left. Or are you saying to go right?
They go right. Oh, wait.
You're right. Okay, if they go this direction, which are they going towards? They're going towards, yes, that's the right.
Oh,
Touche. Which carbonyl are they going towards? The ester. If they went the other way, they'd be going towards the ketone. So why are you suggesting they go towards the ketone? Sorry, the ester. There's more electronegative oxygens there. I think that's a phenomenal statement. Rule 5. There's more electronegative oxygens there. That statement is saying what? Induction. Which means, sorry, you skipped a bunch of rules. Okay? That's a perfectly valid argument. This is typically what students would do. Let's move the electrons that direction. Okay? What happens if you move the electrons that direction? Can you stabilize that negative charge? You know is a good response. Most people go, oh, well, don't you have resonance? No, you've exceeded the octet. Okay, what happens if we look at the other half of this? What charge would we then have on the carbon? No, following the same pattern. We haven't shown the electrons going the other way. I'd have a positive. Can I stabilize that carbocation? So, common misconception. We can do that. You're moving the electrons down because that's positive. You're taking the electrons in a pi bond shared between oxygen and carbon. Which atom is taking those electrons with this arrow? That arrow is showing the electrons going towards carbon. So carbon can steal electrons from oxygen. No, why not? Electronegativity. That arrow is an invalid arrow. You're moving them in a way that is not allowed. Okay? So we don't have good resonance. We end up with two structures that were awful. All of that probably centering on an inductive argument. What happens if we move the electrons the other direction? What would our result be? A negative carbon. Can carbon stabilize negative any better than a positive? This one's better because I can do resonance. Where am I putting the negative charge? On oxygen. That's a good structure. What about the other piece? what charge would be building on that carbon? A positive. Can carbon stabilize that positive charge? Are we ripping electrons away from oxygen by showing this? How many electrons around the oxygen? 8. Did electron or oxygen lose electrons?
You show positive charge, you did, right?
How many electrons around the oxygen? 8. How many electrons around the oxygen to begin with? 8. Did oxygen lose electrons? No. That is a perfectly valid resonance structure, and in fact is an incredibly common resonance structure that is typically known as the acylium ion, which we'll see in the next unit. Okay? An incredibly valid and important one. Well, you're saying, well, didn't you say we couldn't remove electrons over here? Well, what would the result be if we took those electrons and moved them down? How many electrons around that oxygen? 6. Did oxygen lose electrons? Yes. That's why that resonance is invalid.
Why can't you just do resonance the other way? So it's better.
Could I have taken electrons from the other oxygen? Yes. What does that mean about this positively charged species?
Stable.
It's really stable. Where do my electrons go in that bond? Towards the left, just like Beyonce. Or Beyonce's boyfriends. Right? Okay? Make sense? Okay? The exact details behind this, yes, may be insanely difficult and confusing, but you again need to search for your most reactive site and play with the charges. Okay? Is this something I expect you to be able to do? Look at content that you've never seen before, but be able to predict the most likely way that reaction occurs? Yeah. Absolutely. Okay? That is more difficult. You are absolutely capable of doing that. But you have to follow the charges and rules that we've talked about. Okay? Yes?
So why, when you react that with H3O, that occurs?
So why does this happen becomes the next important thing. Just because we can show that we have some stabilization here isn't enough to drive this reaction forwards. Okay? So why is this happening? This comes down to the mechanism. Okay? So H3O plus with an ester, what does that do? As a hint, the answer is on the board. It converts the ester into a carboxylic acid. That's your basic acid derivative conversions. You're responsible for knowing those. You protonate the carbonyl, water can attack. You protonate the leaving group, you deprotonate the water. Dance, dance, dance. Ester. Not ester. Acid. Okay? The fun part behind this isn't so much that we've converted to an acid, but it's now really neat is if we spin that bond, and that's what Cardy's trying to show with that red arrow. We're just doing a rotation. We're doing a rotation to align it up in this case, and you notice there's a massive conglomeration of arrows. A massive conglomeration of arrows that looks an awful lot like Diels-Alder. Okay? That looks like virtually all of our oxidative cleavage mechanisms. Okay? Looks like MCPBA for that matter. Okay? All of those bonds break. The result is that we form CO2. That's what actually drives this reaction. That structure that we drew before with the acylium ion is still positive. It is still susceptible to nucleophilic attack. What happens the instant CO2 is formed? It leaves. Can I reverse the reaction if there's no more reactant? No. The driving force on this is the formation of CO2. Okay? Really, it's the formation of a carboxylate. Okay? And for those of you that wonder, well, how is that a carboxylate? There's your carboxylate. Okay? But what did I do with this carboxylate? I removed it from the structure, right? When we remove things from a structure, we can use a two-letter prefix known as D. I did a decarboxylation. Right? The name gives you some of those clues. Okay? One of the things that is exceptionally deceptive about this is what is the reagent that initiates this? H3O plus and heat. How often have you seen H3O plus as a reagent? Virtually everywhere. It is so deceptively simple as an individual formula that most students freak out and don't understand what to do with it. The big tip-off that you're doing a decarboxylation is not so much the H3O plus, but the H3O plus and heat. If you see that heat, pretty much a guarantee that you're going to be doing some kind of elimination. Wait. First semester, we talked about substitution elimination reactions, and they competed with each other. How did we know we favored an elimination instead of a substitution? Oh, heat. Those patterns still hold true. They give us tips and hints to help us move through. Okay? And again, because it sounds like, oh, someone just sat down and figured this out. No one just sat down and figured this out. Some jackhole took the substance, heated it up with an acid to do something else, and all of a sudden half their structure was disappeared. Okay? Could have even been worse. Maybe they did it in a closed system. What would have happened then? Why would it have exploded? Because it formed a gas. The gas caused a buildup of pressure, which caused the system to explode. Okay? Somebody probably colossally screwed up, and this reaction was discovered. Okay? We now talk about, well, why did that happen, so that we don't make that same colossal screw up. Okay? The next little fun part to address here, just because CO2 is stable doesn't mean the reaction has to happen. What else also has to be true? The other half also has to be stable. Is this structure stable? Yeah. As a neutral structure, it is stable. It is an enol. What does the enol do? Revert back to the keto form. You mean enols show up again? Yeah. Okay. For those of you moving into biochemistry going, God, I hope I never see this again. Literally, this is what happens in biology too. Same reaction. Okay. You need to be cognizant and looking for that enol conformation. It shows up a lot of different places. It is one of the reasons why we can cleave carbon-carbon bonds. Okay. So, how does it all get strung together? We can start with our malonic or our acetoacetic ester, add just a standard normal base. Okay? Because the alpha position is more acidic, because there's two resonance stabilizations, I can use that weaker base. That gives me my nucleophile. The nucleophile can attack an SN2 reaction, which attaches my piece to it. I can then follow that up with base, if we're trying to be kind of nasty about hiding that chemistry. Base in water is going to do what? The same thing as acid in water does. Convert the ester into a carboxylic acid. Follow that up with sulfuric acid or H2SO4. And now you go, well, I don't have H3O plus anymore. Focus on the chemistry of those reagents. H2SO4 gives you H plus in the presence of H2O. There's our H3O plus. Notice you have the delta symbol, we've got the heat, we're doing the decarboxylation. Okay? Not anytime you have heat. This is kind of a horrible example, but we're going to do it. Do I get the decarboxylation?
Without the E? Where?
I did a quick adjustment in the structure. Would I expect to get a decarboxylation, which in this case would just mean deleting that? Would this reaction happen? No, why not? Wouldn't I get CO2 as a leaving group?
So you need to stabilize the negative charge.
Remember, there's two pieces, CO2 and the other half. I would form a negative carbon. Is that negative carbon stable? No, which means it can't break. The bond to CO2 never breaks, and I'm left with the acid. Nothing changes. So it's not just heat. I have to have that positioning. I have to have, the potential for an enol to form. No enol, no decarboxylation. Okay? Malonic ester synthesis does the same thing, okay, except in this time it's the diester as opposed to a single ester. Nothing particularly new or different or exciting about it happens. Notice we do still keep a carboxylic acid. We lose only one of them. Why do we not lose the other one? Why does that structure not come flying off? What would be left here? That would be a negative carbon with no way to resonance stabilize through an enol, which means I can't eliminate that other one. It stays there. Right? It is the conjugation, or it's not quite conjugation, but the proximity of those two carbonyls, okay, being exactly one alpha carbon in between. You need both carbonyls to initiate this. And one officially has to be an ester. Okay? Protecting groups, your textbook talks about them. Yay, protecting groups. Okay? From the old slideshow, if you take a look, there's now a sequence of a whole bunch of other slides that do not start with this slide. That is because those are all optional slides. If you're interested in biochemistry or protein synthesis, take a look at it. If you're not, don't worry about it. Right? I would kind of argue that nobody should be interested in that until after the final. After the final, feel free to do whatever you want. Okay? Which gets us to the new material. In our new material, we're looking at a new functional group, quote unquote. We're looking at aromatic rings or benzenes. Okay, which means we're going to have a new nomenclature system come up. You'll notice aromatics do not show up on our list. Okay? They're their own kind of entity. We typically reference the aromatic ring as the longest chain, okay, and we'll call it benzene. There's another name we could have called it. What could we have called that? How many carbons are there? 6. Because it's cyclic, I could call it cyclohex. Cyclohex. Triene. And in fact, I would probably have to get a bit more specific there and call it 1, 3, 5 triene. I haven't dealt with the chlorine yet. We're just talking about benzene.
Yeah, nobody wants to do that.
Okay, nobody wants to do that. Don't call it benzene. Or sorry, don't do that. Call it benzene. There was a comma. Right? So what would be the name for this first compound then? Well, the longest carbon chain is benzene. Is there a substituent on it? There's a chlorine, which is called chloro. Where does my substituent always go? Position 1, which means done. Chlorobenzene. How about the next one? Nitrobenzene. Done. Okay? So the nomenclature system for our benzenes is relatively simple. Okay? We're just naming the piece attached to the benzene. Okay? They can get more complicated, but for the most part, that's where it centers. Okay? Along the lines of getting more complicated, there are a bunch of common names. Okay? For instance, you might have heard of toluene. What is toluene? Okay, it's a benzene with a single carbon. So it would be methylbenzene. Why do we call it toluene?
Because it's generic.
Common name. Okay? For the same reason we don't call it dihydrogen monoxide. Okay? So there are a bunch of aromatic compounds that have common names. Toluene, phenol, anisole, aniline, benzoic acid. Okay? They're borderline. They are officially common names, and you should not have to memorize them. That doesn't mean you won't see them. Okay? So be aware of that. TNT is explosive. TNT stands for? Not quite tetra. Tri. Nitro. Toluene is TNT. Right? It's usually used in mining. I don't think it's used in mining anymore. It's dynamite. So there's toluene. I now have a trinitro, which means what needs to happen? NO2. 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 Was that the only way I could have done it? No, there's a bunch of different ways I could do it, which means I would need to come up with a nomenclature system to reference that. That nomenclature system would be pretty phenomenal if I used the same nomenclature system I've used in the past, which would be numbering. Where does my numbering start? Highest priority functional group, which is the base name was toluene, which means the highest priority functional group is the methyl. So this TNT would be 2,3,4 trinitrotoluene. Okay? So we have to specify those locations. What we'll find is there's another way to specify those locations. It is not officially IUPAC. IUPAC is directly referencing the numerical arrangement of those. Okay? Aromatic compounds, there's a variety of ways you can see their signals show up in IR. I tend to frown upon looking at it because for the most part, they're hard to see. Okay? More examples. Take a look at the far right here. You could see these patternings for those particular substitutions. So if I had a hexachlorobenzene, I would expect this peak patterning. Where would I find that peak patterning? 2016-67. Okay? These peaks are all relatively tiny, so they become very difficult to analyze and they're hard to find. If you know what you're looking for and the spectra came out clean, you could find them. Okay? That's all I'm trying to tell you. For the same reason, 900 to 700, you could do the same thing. You can try and find peaks in there. Is there...
Yeah, do you mean intensity or do you mean...
thickness? Intensity. Intensity.
Okay.
Right. What you're looking at here for breadth is if you wanted to, you could come up with what are those, each of those little lines mean. Okay, you're only 2,000 to 1,600. They're probably what, sets of 50. So those are very, very narrow peaks. Okay. NMR spectroscopy. Okay. If you see something show up in your NMR, in HNMR in the 7 region, you should be happy because that's an aromatic ring. That very quickly nails down at least 6 carbons. Okay? Based on the number of hydrogens, which would be the integration, the area underneath the curve, you could determine how many hydrogens were on that aromatic ring. Based on the splitting pattern, you could come up with the substitutions. What this is trying to show is how you could look at that. All of those things should be relatively quickly derived because you've done practice with solving aromatic spectra. For that practice, all you got to do is go to Google and type benzene compounds NMR, and you will get tons of different examples. Okay? If you don't want to deal with spectroscopy, that is your choice. It makes up less than 10% of the exam. Okay? So, you all watched the video on a summary of rules. We'll talk about aromatic, okay, or aromaticity. So you have aromatic compounds, you have anti-aromatic compounds, and you have non-aromatic compounds. Okay? Why do we need 3 categories? It's partly addressed in the video. Certain conditions address certain things. Okay? Aromatic have to satisfy 2 criteria: a fully conjugated ring with overlapping p orbitals. Okay? P orbitals can be tricky because they can be generated through resonance. So you could look at a structure and be like, oh, there's no p orbital there, but you probably ignored the resonance. And when you move to the resonance, ta-da, there's the p orbital. So what you're looking for is not necessarily p orbitals, but sp2 hybrid atoms. Because if you have an sp2 hybrid atom, what does it have left over? 1 p orbital, which could now be conjugated through the system. The next part is it has to meet Huckel's rule. Huckel's rule is an odd number of electron pairs. Everybody gets confused by this 4n plus 2 total pi electrons. N is just 0, 1, 2, 3, 4. Okay, 5, 6, 7, 8, all indefinite. Okay. It's a formula for you to go through and calculate. Since people get kind of stumped by that, let's switch this up a little bit. Okay. Pi electrons. So let's just focus on our total pi electrons. Is it aromatic if you have 2 pi electrons? Yes. What would N be if you had 2 pi electrons? 0. So 2 pi electrons, and we satisfy rule 1, aromatic. How about 6? Where N is 1. 4 times 1 plus 2 is 6. What's the next one? 10. Next one. 14. 18. When do we stop? You keep going forever. Okay. Yeah, your N has to be whole numbers. Okay. They can't be decimals. Do we really want to have to memorize this pattern on forever? We have 4n plus 2. Okay. How many people were happy with 4n plus 2? Okay, 2 people. Is there another way we could do this? To get up to 18 or 22 electrons, is that a lot of electrons? Is that going to be difficult to count? If it's difficult to count, guess what it's also difficult to do? To draw it. Which means it has nothing to do with frost circles. If it's difficult to draw, am I going to ask a question about 22 or 18 electrons? No. Whoops. I would argue you could probably get away with 2, 6, 10. 14 is kind of borderline. Okay? Once you've got that, you're probably set for most of your questions. Okay? Anti-aromatic satisfy 2 criteria as well. We have the same rule number 1, overlapping p orbitals. But rule 2 changes. Now you get an even number of electron pairs, which means when we look at our total electrons, what are our total electrons? Could we have overlapping p system or pi system with 0 pi electrons? No. So 0 doesn't count. 4, 8, 12. Okay? Again, I would argue 3 is a solid memorization and you're done. Okay? It's your alternating even numbers. That works to set up aromatic versus anti-aromatic. Okay? The last one, non-aromatic, it invalidates the rules listed above. Okay? Or it's a trick question, which are always really irritating. You can tweak the structure to be anti-aromatic. Okay? So there are weird kind of exceptions behind these. Aromatic, very, very stable. Okay, which is why when we talk about benzene rings, what do? Nothing. Anti-aromatic structures are non-stable or unstable. How many of you are standing up right now balancing on one foot? No one. Why? that would be unstable. So what do you do as a person? You adjust your structure to make sure that you are not balancing on one foot. Compounds can do the same thing. They will adjust their structure so that they become non-aromatic. Okay? But there is a system where you could tweak the structure or force it into a system where it would become anti-aromatic. So the non-aromatic category can be tricky. You do kind of have to watch out for it. So, first three were already on the video, so we can go through and look at it. We have aromatic, we have anti-aromatic, and we have non-aromatic. Okay? Why is the second one non-aromatic, or sorry, anti-aromatic? It's a fully conjugated system, but 4 total pi electrons. Okay? Turns out that that structure will actually attempt to equate to non-aromatic. Why would it attempt to do that? Because an anti-aromatic structure is unstable. So that structure will actually bend a little bit so that the p orbitals don't overlap. If they don't overlap, it's non-aromatic. Okay, so that's where that trick can kind of come into play. The third one, why is that one non-aromatic? We have an sp3 atom. A lot of students will go through and just say, which one do I have every atom with only 2 bonds? Yeah, every atom has 2 bonds, so we're good, except for that top one has 2 implied hydrogens, which makes it sp3, no conjugated system. That one's non-aromatic. The next one, anti-aromatic. Why is that one anti-aromatic? It's fully conjugated. We still have that carbocation with that p orbital, so that one counts. Right? 4 pi electrons, again, anti-aromatic. This is, again, kind of a weird, tricky one, because that could potentially say, I don't want to be anti-aromatic, and what does it do with that last carbon? It'll push it out of the plane so that it's no longer overlapping. So it'll change the chemistry of the structure. Next one. 6 pi electrons, so that should be non-aromatic because it's not cyclic. It must be a cyclic system. Fully conjugated means cyclic. So that next one is non-aromatic. The next one. Answering wrong now is a good idea. Why is that one aromatic? I only see 4 pi electrons. The oxygen can do resonance, which means I can count a pair of electrons from the oxygen and I get 6 pi electrons, which means aromatic. Pretty much. Why did we not call that one 8? Aren't there 2 lone pairs on oxygen? Well, the red electrons I circled and said those were fair game. Why can't I do the blue ones? Everybody's favorite answer on this one. What's that? No, it's absolutely not empty. That's why there's 2 dots. The red and the blue orbitals are perpendicular to each other. Once you do one, the blue one is now perpendicular to the pi system. It can't do resonance. It's in a perpendicular orbital, which means no orbital overlap, which means no resonance. I can only do 1 lone pair at a time off of a given atom. You won't. It doesn't match either of those rules. You can talk to me after class. Last one. Okay, you're saying aromatic because pi, pi, and lone pair, right? What about the blue lone pair? Why can't those donate in? Perpendicular orbital. It is perpendicular to the pi system, which means I can't count that. Okay? Can only count one of those lone pairs. That one comes in as aromatic as well. So it's not just, oh, there's lone pairs, I can count them. They have to be in a perpendicular orbital. For those of you that have a hard time seeing that, I do not blame you. It is very difficult, and it relies very heavily back on atomic theory back in Unit 1, okay, or first semester, sorry. Okay, Unit 1 of first semester with molecular orbital theory. If you have a hard time with it, fudge it as best you can. sp3 atoms, you can count one lone pair. Why can I not count the blue lone pair? What is the hybridization of that nitrogen? sp2, which means can't count that lone pair. You should be fairly confident with hybridization. You do see questions as simple as, what is the hybridization of this atom? Okay, that should be a quick pickup. I've got an answer in seconds on the ACS. Okay, and we can review that. Hopefully, in theory, we'll get time to review, but we still got a lot of slides to get through. Okay, so if you're unhappy with the page,